So in our last lecture, we discussed that how to design the control gain K so that the matrix A minus lambda 2 bk until n minus lambda n bk are stable matrices. So we know if all the matrices A minus lambda I bk are stable matrices, then as t goes to infinity, so this block, the exponential of a minus lambda 2 bk, then a minus lambda n bkt can be written as a diagonal matrix. We have EAT, so EA minus lambda 2 bk until exponential of a minus lambda n bkt. You know, as t goes to infinity, so this term will convert to 0. So this term will convert to 0 exponentially. So as to get to infinity, the middle part will be a block diagonal matrix. We have 0 block. Sorry, it's not 0 block. We have exponential AT, then 0 block. So what's the matrix P? We know matrix P consists of all the eigenvectors associated with each eigenvalues. So P, the first column will be, let's take P as the R1 vector. Then we have P2 until Pn. So when P is chronic I, so every entry is multiplied by I an identity matrix. So here identity matrix, then P2, Pn, chronic I. Identity matrix. Then we have some other matrices. Okay, let's P bar 2 until P n bar. Okay. Let's assume we know the P inverse. The P inverse contains the left, each row contains the left eigenvector associated with each eigenvalue. So that's Q1 is the left eigenvector of the Laplace matrix associated with 0 eigenvalue. We have Q1 transpose, then we have Q2 until Qn. So it's chronic I. So we have this Q, I say Q1, 1, chronic I, then Q1 n chronic I, then have the Q2 until Qn chronic I. Q1, 1, and then the matrix until Q1 n. Then we have big Q2, big Qn. Okay. So if we use the first row, so this is P, and this is P inverse. So we will need to weight the Q matrix. So Q transpose Q1 transpose R1 vector will be 1. We use first row times the first column. It will be first row times the second column is 0. It will be all 0. So the second row times the first column, same using last row times the first column, then the last row times the second, then the second, third, and n columns. Now let's copy it here. Q11 I, Q1 Ni, big Q2 into big Qn. Now let's see, we have Q11. If you use the first row times the first column, so EAT, first row times second column, so Q2 EAT. Because here we wrote Q1 as Q11, Q12 until Q1n. You have Q1n exponential AT. The same for the second row. Last row, Q11, Q12, Q1n. And here we times x0, 0 x1 0 until xn 0. Then as we see, all the rows are the same. This means all x1t, all x1t until xnt, they will convert to the same value. So for any xit, it will convert to exponential at, so q1 1 times x1 0, then plus exponential at Q1, 2 times x2, 0 until exponential EAT Q1n times xn 0. Then xit can be written as EAT, then Q1 identity matrix, Q2 identity matrix, Qn identity matrix, then x1, 0, x2, 0, till xn 0. So can be written as Q11, Q12, Q1n can be written as, so this part can be written as Q1 transpose chronic identity matrix. So in conclusion, all the xi we will convert to the exponential of AT, then Q1 transpose chronic I x0. Let's notice that Q1 is the left eigenvector of the Laplacian matrix L associated with 0 eigenvalue. So then we need to normalize Q1 by the sum times R1 vector is 0. So this is for undirected and connected graph. The result is very easy to extend it to directed graphs. So all it follows, the only thing you need to take care of is how to design the controller gain K for directed graphs. For agents with linear dynamics, it is the general case. It includes some dynamics we talked about before as special cases. For example, double integer dynamics and single integer dynamics. So we know the xt xit will convert to exponential at, q1 chronic identity matrix, then x0. So q1 is a left eigenvector of the Laplacian matrix associated with 0 eigenvalue. So q1 is normalized times R1 vector is 1. Two conditions. We know for double integrated dynamics, so we have xi dot is vi, so vi dot is ui, so it can be written as xi dot vi dot 0 1 0 0 xi vi plus x1 then UX. Suppose the controller is well designed, in this case, the A matrix is this one. Yeah. If the control law is well designed, then we can show the exponential EAT will convert to this matrix. Then XIT will convert to this matrix times Q1 transpose, then chronic I. Then for undirected graphs, we know the Q1 will be 1 over n, 1 over n. Then for the Davinci dynamics, then we have T 0, 1. Then we have the Q1 will be 1 over n I2 by 2, 1 over n I2 by 2, 1 over n I2 by 2. So it will be the average of the position, average of the velocity. Yeah. This side will be XIT, VIT. Then we know the XIT convert to the initial average plus T, the initial velocity. Velocity will convert to the average. Okay. Here, this is X0 bar. This is V0 bar. So we see the result is the same with what we discussed for double integral dynamics. Then for single integral dynamics, if the A matrix is Xi dot UIT can be written as 0 times XIT plus 1 times UIT. So the A matrix is 0. Then the exponential of AT will be 1. So XIT convert to. So here's 1, has Q1. So if dimension is 1, so it's just Q1. It's chronic. Yeah. The scalar. So it will be still Q1. Q1 transpose will be times X0. So we know Q1 is just 1 over n. 1 over n. So it will be the average of the initial state. So X bar 0 will be 1 over n sum I from 1 to n xi 0. The dimension, the small n is 1. The dimension of the A matrix. Here n is 1. So the capital N is the number of agents. At this point, we finish all the basic consensus algorithms.